Thanks, Elsa, and thanks everybody for listening in. Before I get started, I want to talk about my collaborators that include former graduate students and postdocs, and a long list of people from the PPL group. And at the top of the list are people who've done work with me this past year, which I'll describe in my talk. So when I come here, I always get asked questions about cosmology, so I want to give a little overview of how we do computational cosmology, and then a little bit of talk about using blue waters and what we'll be doing with blue waters in the coming year, and then go over some of the details of ChaNGa and improvements we've been making. Okay, so recent result in cosmology. Less than a month ago, the Planck collaboration put out this map of the universe. It's a map of the universe when it was only 300,000 years old. This is the map of the entire sky. The colors represent fluctuations in temperature that come out of the Big Bang, and it's from those tiny fluctuations, which are only 1 part in 10 to the 5, that things collapse and make the galaxies we see today. We can get some very important information about the universe from this map. And one of the things they published that they derived from this map is what the universe is made of. A large chunk of the universe is what's called dark energy. Yeah, we don't know much about it, other than it completes the energy density of the universe. Another chunk which we know a little bit more about is called dark matter. This is stuff that gravitates like ordinary matter, but it doesn't interact with photons. It's dark. And then there's this tiny slice here that's labeled ordinary matter. Physicists would call this baryons. This is things like hydrogen, helium, oxygen, carbon, kind of things you're made of. And so the questions we want to ask from computational cosmology is, what is this stuff made of? Can we put constraints on that? And how does it interact with ordinary matter? And what does that tell us about, again, the overall structure of the universe? One of the early successes of computational cosmology was pointing out that this dark matter cannot be the things we know of as neutrinos. Essentially, neutrinos, as are produced in nuclear reactions, are too light to be this dark matter. They move too fast. They would wipe out the structure that would make galaxies. And so we have this other list of candidates of dark matter, which is beyond the standard model particle physics. And actually, one of the disappointments about the Large Hadron Collider is, although they discovered the Higgs boson, they have not yet discovered the dark matter particle candidate. Perhaps in the future, and perhaps cosmological simulations will shed some light on that. Okay, so this is the universe at 300,000 years. This is the universe today. This is a map of galaxies from the Sloan Digital Sky Survey. You are here, and you're looking below and above the Milky Way's plane, and you can see the structure of galaxies, and you see that there's sort of soap bubble-like structures there. The sizes of those things compare to the sizes of the lumps you saw in the Planck map, and we want to relate those two through following the evolution of the universe over 13 billion years. But as well as modeling the dark matter, we want to make sure we form these things. Okay, so this is actually M51, the Whirlpool galaxy, but it's a good proxy for the Milky Way. And if this were the Milky Way, we would be living somewhere out here. Okay, and furthermore, what you see in this picture is not the dark matter. It's stars shining. You're seeing gas. The red regions are ionized hydrogen. The blue regions are dust. And we'd like to model the physics behind that as well. Okay, so in an overview, we start out with those 10 to the minus 5, 1 part in 10 to the minus 5 fluctuations. We follow them through this nonlinear gravitational collapse, and then we try to make predictions about, for example, the distribution of galaxies, the light distributions within galaxies, and try to put constraints on the parameters of the universe. The further complication, just to demonstrate how nonlinear this is, okay, so here's a piece of the large-scale structure. You see some of these voids and filaments. A single galaxy is shown here. You blow it up, and a single galaxy is surrounded by a roughly spherical dark matter halo with some substructure, and then if you zoom into the very central 1/10 of that halo, you will get this disk of gas and stars and gas, which produces the light that we observe. So you've got to follow this extreme range of scales down to get an individual galaxy. And furthermore, the substructure in the dark matter halo is this very self-similar that produces lumps all the way down to perhaps solar system size lumps, which we have to model. So that gives you a number of computational challenges. First of all, the dynamic range. Uniform volume of the uniform sample of the universe, you have to cover roughly 100 megaparsecs, where the space between individual galaxies is 1 megaparsec, and the size of the visible galaxy is only 20 kiloparsecs, and we want this resolved within that, and so we have that range of scales requiring some sort of adaptive hierarchical gravity solver. Furthermore, there's this temporal dynamic range. Star formation happens on roughly 1 million year time scales, and we really do have to compute for the age of the universe. And so we need adaptivity in time as well. And then what makes gravity hard is that it's long range, right? The force from a shell of mass does not decrease as you move away as you make the shell larger. And so you need to propagate that information across processor domains. And just to emphasize again, if we look at the galaxy in light, in baryons, the galaxy looks a lot different in the dark matter. And so following the baryons is important. I like baryons. Some of my best friends are made of baryons, and so we've got to follow them. How do we do that? The baryons actually obey other forces besides gravity, something we call gastrophysics, but this is hydrodynamics, the physics of star formation, and supernova feedback. First of all, gas dynamics. We use something called smooth particle hydrodynamics, basically because of its Lagrangian nature. It's able to follow the flow. The thing to remember about doing galaxy gas dynamics is that the sound speed in our galaxy is roughly 10 kilometers a second. That's kind of fast, but the whole galaxy is first circulating at 200 kilometers per second, and then the galaxy as a whole is moving with respect to the rest frame of the cosmic microwave background at perhaps up to 1,000 kilometers per second. And so you want to use a method where you don't have to worry about advecting gas through your grid at 1,000 kilometers per second. And furthermore, we're using a particle method for gravity, and smooth particle hydrodynamics is a nice complement to do the gas dynamics. I mentioned star formation. We actually don't know a lot about star formation. Furthermore, we still don't have the resolution to follow it because it happens on sub-parsec scales. And so we have this subgrid model where from our gas, we identify regions that are above a certain density threshold and perhaps contain some molecular gas. And we have a prescription which turns it into stars in a dynamical time. We know how long stars last. And after a certain number of years, they go supernova. If they're over 8 solar masses, they go boom and produce what astronomers call metals. That's anything heavier than helium. So oxygen is a metal, according to astronomers, that pollutes the intergalactic medium. Furthermore, those supernovae also inject energy. And so we follow a blast wave solution of the 10 to the 51 ergs that a supernova injects into the surrounding gas. And so all this is going on, stars produce, feedback happening in order to model a full galaxy. And we've been successful in doing this, in producing realistic looking galaxies. And a movie always helps. So there's the Big Bang. What you're seeing there is the gas. And as the gas collapses, stars form, and occasionally a supernova goes off, which causes a blast wave in the gas. Again, the green color is the gas, while if you see a red and blue tint, that's the stars. The galaxy formation is hierarchical, right? First one lump forms, and then other lumps continue to fall in. As the lumps fall in, you get these bursts of star formation, and you see winds being driven out of the galaxy. Following all this physics is very important in getting the final angular momentum distribution and mass distribution in the galaxy as we see it today. This simulation is actually a small simulation run by ChaNGa on the Gordon computer at San Diego. Okay, so that's one galaxy. We should do more than one. We'd like to do these galaxies. Gee, I should turn the lights off again. So this is a image produced by the Hubble Space Telescope. It's called the Hubble Ultra Deep Field. Hundreds of hours of space telescope time went into this. All the little smudges you see here are individual galaxies with hundreds of millions of stars, but they're galaxies when the universe was only about 1/10 its current age. It's kind of cool. What would it be like if we could see Sanjay when he was only 5 years old? But we would learn a lot about Sanjay if we could see him at 5 years old, and we'd learn a lot about the universe as we study these galaxies when the universe was so young. But we need to understand the physical processes that went into building these galaxies and what these galaxies do to become the galaxies we see today. And that's what we'd like to simulate on the Blue Waters machine. Basically simulate this entire field with enough resolution, with the same resolution that I showed you in that movie, to answer these questions that I just discussed. And our allocation currently is 300 million core hours to do this project. Now on to the code. Call it for ChaNGa for charm n-body gravity. Here's some of the features. Periodic boundary conditions are needed so we can do a subsample of the universe. Somebody already mentioned we use the char migration facility to do the checkpointing. The visualization you saw was produced in real time as it was running on the machine. Very handy for understanding the dynamics. In the construction of the code, we incorporated a number of latency hiding capabilities. First of all, as a standard charm++, you over-decompose the problem, and therefore while one char is waiting for communication, another char can be doing work. We call those our chars tree pieces. But even within a tree piece, we subdivide the work into multiple pieces that can be run concurrently, including the gravity, the smooth particle hydrodynamics, and this is periodic force calculations. Another technique we use is prioritizing certain messages, particularly critical data requests get run with higher priority. Diagrammatically, it looks like this. We have a number of tree pieces. There is work, global work of doing the global tree, other processes that give you forces, local forces, and we had a similar problem that Brian has with his ghost cells. As we over-decompose, there's common data that we don't want multiple copies of, and we handle that through what we call a cache manager, which is local to a processor, not a char. And that way, this cache manager can hold all the remote data that the chars need, and we don't have to replicate it. What this looks like as it executes, here's a projections plot. This is only on 768 cores of Lone Star. You see there's several phases, but here, okay, load balance phase, there's an issue here in that it's taking a while. Building the tree. The first thing that has to happen, well, you see the various stages. The red and the yellow is communication work that has to be done as the global tree walk tries to get its data in order to calculate the forces. There is some latency involved here, and that is filled in at this point by local work. And you see, with this particular simulation, there's more than enough local work to hide the latency caused by the communication. The gas dynamics is actually a lot more communication. This one is run on blue waters, actually, with 1,000 cores. We see communication that's needed by the gravity walk. There's a lot more communication that is needed as the smooth particle hydrodynamics tries to find basically neighboring particles to compute with. But again, that is overlapped by some of the local work, although not completely. This is some more smooth particle hydrodynamics work. Probably there might be a synchronization issue, which we don't understand there. How well does it scale? This is a scaling plot for blue waters running out to 8,000 cores with only 3 million particles. So these are strong scaling results. So the good news is that the actual gravity time is going down nicely. The bad news is that the other parts of the computation, including load balancing, is actually not scaling at all, basically because it's running in serial It'd be nice if we had a parallel language with which we could write the load balancer in. Oh, wait. At any rate, Harshitha is actually working on distributed load balancers for this problem, which would address that issue. And this is just a summary of the work we've been doing over the past year. That the star formation and feedback is a new feature that I put in, ported from our legacy code. We've been working on SMP awareness now that we've got these 32 core wide nodes. We use the charm feature, hasn't been mentioned. You can have a node group and a group to separate out things that are common to a node versus a processor in charm. I mentioned load balancing. Another thing is eliminating some of the global reductions, which came about because I started out as an MPI programmer, essentially, and reducing some communication bottlenecks. Load balancing. Although we're not keeping track of communication, we do have a nice proxy for communication, and that's the distance between the tree pieces. Here's a particle distribution where you see various clusters of galaxies. Here is the, if you can see it, is the distribution of chars in that same space. And so we know that chars that are close together will do a lot of communication, so we use a ORB decomposition to put spatially contiguous chars on the same process. And the coloring over here is by processor number. And so you can see the lower half of the machine is over here, the upper half is over here. You see this one is divided in two, and you can see a cluster of chars in that in this cluster of galaxies. And that's how we try to minimize communication. That still needs some work, essentially because these chars in the cluster are actually doing quite a bit more work than chars that are out in empty space, and we need to balance that a little bit better. I'm getting close to out of time, right? So let me, communication load balance is one interesting thing that Harshitha has just worked on. We saw this rather disturbing. So the colors are a little bit different, but the same idea. There is, by the way, this is 50 million particles on 16K cores of blue gene Q. There's first a lot of communication that goes on as you get data for the global walk, which is in purple in this, and it's somewhat compensated for by local work, but there isn't enough local work. There's this big gap of idle time here. And what's going on? What we noticed was that particular processors were getting a communication imbalance. They were getting a lot of messages. And so what Harshitha did was to actually replicate those chars which were getting a lot of messages. And after replication, there's a little extra work for doing the replication. That's this dark purple here. But then with the replication, the global work can be done a lot earlier. There is some local work that has to be overlapped, but the overall load balance is much better, and we've eliminated that big gap of idle time. And and here's the culprit. Total messages received as a function of processor number. You see that originally there was these spikes up to 50K messages. After we do the replication, we've got the peak here is only about 15K messages for some of the processors. So replicating data to reduce the communication load imbalance. We're doing other topics, and again, I'm running out of time, so let me just talk about what we're going to do in the future. There's more physics to be done. Black holes are actually extremely important for the evolution of galaxies. Every galaxy seems to have one of these things in the center, and it seems to have regulated its star formation rate. Something that's going on even as I speak is introducing some radiative transfer. As stars form, they ionize and dissociate the gas around them, and we're putting that into ChaNGa. And that is being helped because, right, it's essentially C++, and I can just pull out legacy C code and plug it in for the most part into ChaNGa. Still thinking about better gravity algorithms, and there has been some work on GPUs. We need to think about that more. And there's other astrophysical problems. Gravity is scale-free. So doing gravitational dynamics of the solar system can be done with this same code. And I'm looking forward to working on that in the future. Also in the future, the simulation I'm doing on blue waters is just a tiny piece, right? The Hubble Space Telescope has a very narrow field of view. What would it take to really do a full simulation of the visible universe? Well, this is about what it would take. Roughly an exaflop year. Okay, so that was why I was asking questions to the panel about what's going to happen with exascale. And we really do need this because we are going to have future surveys in about the same time frame. LSST is planned to come online around 2018 or so. At that time, we should be doing simulations that can address that survey. Just in summary, the kinds of things that CHARM Plus has that made this application possible. I don't need to repeat. You've seen all this before, but all of these features have been important for us. So in summary, cosmological simulations, they're interesting in their science, but they also make interesting computational challenges, particularly because of their non-local data dependencies and because of their hierarchical nature in both space and time. And I've been actually very happy with the performance that we've been able to get out of ChaNGa and applying it to our problems. And last of all, if any of you are interested in doing computational cosmology yourself, we have made it available. And I also want to thank the folks that have funded this work as well. So thank you.
Questions for Tom?
So one exaflop year once and you're done. The whole cosmos never have to be simulated.
Well, then we say, oh, we need a different type of dark matter. All right, so then we do it again.
Any other question?
Can you talk about the performance improvement when you enable SMP mode of CHARM++?
We're actually still working on that. Pratish is probably working on it as we speak. So at the moment, we've been using SMP to reduce the amount of intra-node traffic. That is, all data accesses within a node are done via shared memory rather than the CHARM messaging system. So it's fewer messages within the node. My guess is, and this is still a guess because we haven't fully implemented it, but my guess is that message spikes, or basically the total amount of messages should drop as we go to, say, an SMP cache, because at the moment each core has its own copy of external data. If we make that node wide, that would drop the amount of external communication by 1 over the number of cores in a node. But that's still speculation at the moment.
More questions? Okay, let's thank again our speaker.